Be opening with Summer School Arithmetic Geometry, supported by the Clay Mathematics Institute. And first I want to give the word to the scientific director of the Clay Mathematics Institute, David Elwood.
Well, thank you very much, Yuri. It's a great pleasure for me to be here. When I was a graduate student, I went to many summer schools like this, although there were less of them at that time than there are today. And I love these things, and I hope that you'll have a fantastic time while you're here. Just trying to orientate this correctly. Okay, that should work. I'm not going to take much of your time, but I'll just say a few things which I hope are useful and introduce all the really important people who are actually going to be talking to you and making this school really happen. The first thing, since I'm from the Clay Institute, I have to remind you that it's extremely important to submit your travel reimbursement forms, and I think you can begin doing that from lunchtime today. So take care of first things first. Talk to the wonderful staff we have here. We have Elizabeth from CMI, so she's come over from Boston to make sure that she can help you and we get everything straight. And we also have Claudia and Sylvia. I'm afraid I've forgotten your family names, but they're the people who've done a tremendous amount of preparation in making this school happen. And they're somehow the unsung heroes of many activities. And so be very, very nice to them. They've been working very hard for you for a year in preparation for this school. So they'll be here to help you, I think, from lunchtime onwards with processing those travel requests and get them in as soon as possible. There's a few of you which are self-funded. Unfortunately, we didn't have our funds. Even though the Clay Institute has a large endowment, it's not enough to do all the things that we'd like to do. And some of you here are self-funded, and I'm afraid I have to apologize that you've slightly overpaid. So if it's good news, you'll be getting a little bit of money back. And so you can also talk to the staff here about arranging that in a form which I hope is convenient for you. It's somehow my role as research director of the Clay Institute to say a few things about the Clay Institute. The Clay Institute sponsors a variety of activities. We're really, although we have a base in Boston, we're really an institute without walls. So we prefer to go to certain locations where they can best support the activities which are most valuable at any particular time. So we don't confine ourselves to a particular location, but we like to travel around. And it's an absolute delight to be here in Göttingen, a place with a fantastic mathematical legacy. And I hope that you're really going to enjoy and be very inspired to be here for 4 weeks. It's a tremendous opportunity. CMI sponsors research from high school right through to senior scholars. So there are many, many opportunities for all of you to have contact with CMI throughout your career. And of particular relevance to you are programs like Liftoff. That's a program which supports you when you finish your graduate studies and gives you some support in the summer when you graduate so you can travel around. And it's one of the tragedies of the current American funding system that many people end up without funds the moment they graduate in that gap between before they begin their first position. We have some fantastic postdoc positions. They range from 3 to 5 years, and they're called the Clay Research Fellows. So essentially, it's a postdoc position that will support you to do whatever you want, go wherever you want to go for an extended period of time, and which best suits your research. So they're worth looking out for and definitely worth applying for. I think we award between 2 and 3 of those every year. So there's only very few of them, but they're fantastic positions if you can get one. We support lots of other conferences and workshops in part. The summer school is CMI's largest single budget item. So, but we also collaborate and help, if you like, give seed funding to many other conferences and workshops. So we try to do as much as we can in that direction. One thing that's unusual about CMI is it's permanently endowed by a single family. And that might sound a little bit scary, but since they handed over the money to us, essentially it's a mathematics institute run by mathematicians for mathematicians, and it's almost unique in that respect. So essentially there's no government involvement, there's no bureaucracy. Whatever our board of mathematicians feels is important, that's what we try to do. In fact, one of the motivations of starting CMI was to counterbalance certain trends, which seem to be important to mention because they're becoming, have a stronger and stronger influence in mathematics. And I noticed this right down to the high school students I meet in a high school program that we run actually at CMI. So the funding structure of many organizations encourages people to seek out, short-term goals, to write as many papers as you can, work on the easiest problems you can find. And I have nothing against you working on easy problems. And you should definitely solve all the easy problems that you can, but with a view towards working on hard problems. So I'm not saying don't, write as many papers as you can, don't not look out for the easy problems, but also don't forget about the hard problems. Because one of the remarkable things about mathematics is it's driven not only by, if you like, the applications to the real world, which is something that's very well understood by governments and other funding organizations, but it's also driven by some key problems in mathematics. And one of the strange things about mathematics is that these key problems somehow tend to get forgotten. And one of the motivations of one of our most misunderstood activities was this Millennium Prize Problem event that we held in Paris in 2000. The motivation there was not to talk about million-dollar problems, but it was really to stress that mathematics is also driven by focusing on sometimes problems which are out of your reach, but they're problems which have given enormous stimulation to mathematics and which drives the development of many tools and techniques which will be of great benefit for the future of mathematics. So don't forget about the hard problems and long-term goals. And just to set the record straight, the idea of putting $1 million price tag on these problems was really to stress in contemporary terms to the broader community that mathematics is of importance for its intrinsic value. These problems have value themselves, not just the applications which kind of also drive the development of mathematics. So, everything in today's world, from a Van Gogh to a piece of mathematics, can be somehow understood. Its value can be understood in contemporary terms by putting a price tag on it. These problems are, of course, worth vastly more than $1 million to us as mathematicians. But it makes a point which many people can understand. Some of the other things is that I hope that, like I said, this summer school is our largest single budget item. It's almost 10% of our annual budget. And it's important that we do this because, this is a very, very special time of your career. This is a time where you can devote your undivided attention to your research. And I hope that it was certainly true for me, and I hope it will be true for many of you. The contacts that you make both with your peers and the lecturers and colleagues that you meet here will be of tremendous value to you throughout your career. So don't be shy. Ask as many questions as you want and talk to as many people as you can, because somehow, we're brought up in a very competitive environment where we're kind of rewarded for beating out the other people. But the more you can share what you know and what you learn, the greater that the greater that mathematics will prosper from that. And I think the more success you will ultimately have. So yeah, that's kind of what I wanted to say about the big picture. Your role is really not only to master what you're taught here, and you're going to have some of the world's finest experts on the field lecturing to you over the next 4 weeks, but you're also the inheritors of a fantastic legacy of mathematics. And it's an awesome responsibility that you have, not only to absorb all this mathematics, but also to take it forward. And as mathematicians, we're incredibly lucky. CMI is an institution which supports pure research, and there's no immediate advantage to what we do. And we're extremely privileged to have this opportunity to work on something which is so incredibly valuable to society and has really been a driving force for culture over, 3-4 millennia, if you go back to the ancient Sumerian culture. So, the economy of knowledge only really takes off when it's shared. And the real heroes of this event are the speakers and lecturers that are going to be talking to you this week. They give a tremendous amount of their time, of energy, and it's a tremendous generosity that makes this event possible. It's one thing for us to get Mr. Clay to give us some money, and that's tremendously hard. But don't forget that the greatest generosity are the people who have given so much of their research time this summer to spend educating you and helping you with the problems that interest you the most. So be extremely nice to them. Make a fantastic use of this opportunity. Really develop close personal relationships with them as much as you can so that you can continue to benefit long after the school and hopefully throughout your career. So that's all I have to say. It's great to be here in Göttingen. It's great to see you all here, and I hope that I'll be kind of having lunch with you every day, and I hope to move around and meet many of you. If you really like what happens here over the next 4 weeks, and I hope you will, please write emails to that summerschool@claymath.org address, because we can share them not only with the folks here at the Math Institute of Göttingen, but we can also share them with the Clay family. And Landon Clay is remarkably interested to hear, about the effect of the money that we're spending. He doesn't interfere in any way in what we do, but he loves to hear back from people who are involved in some of the activities which we do. So please let us know about that. One final word about Landon Clay. He's kind of a remarkable man. He's a businessman. And when I first met him, I asked him, why do you want to fund mathematics research? I know you studied a little bit of mathematics while you were at Harvard, but you didn't major in mathematics. And he told me an answer which kind of just blew me away. He said, well, a lot of people are trying to leave a legacy in terms of a building or something like that. And that's really good. I mean, buildings are really useful. But, there's nothing I know of which has more enduring value than mathematics. A mathematical equation really lasts forever, and those mathematical discoveries provide both utility and pleasure and enjoyment, forever. So he really saw mathematics in a very sophisticated way as something that could reach into the future, and that if he could contribute in some way to its development and to its proliferation, then he was the happiest person in the world to do that. So don't forget Mr. Clay if you have a good time here. And I promise that I'll communicate to him anything that you send me. So, I hope I get to meet many of you this week, and hope you have a great time. Thank you.
Well, thank you very much, David. Can you hear me? Oh. Before we start, so a few organizational things. Dates for cash payments. July 17th, 1:30 till 2:30. July 18th until July 20th from 9 to 10 and from 1:30 to 2:30. Today at 4 p.m., a lecture about computers at the Math Institute, how to. So we have computer access here. We have terminals in the library, in the Gauss lab, and wireless access throughout the building. So you should be able to access the internet. But you will hear more about how to use computers and about things we have later today. Afterwards, opening reception, barbecue at 5:30 p.m. today and on Thursday. So you shouldn't go hungry here. Lunch. So lunch is served at Mensa. It's a student cafeteria. And we'll meet today at 12:30 after the second talk, right in front of the lecture hall. And you'll be escorted there by our graduate students who are here, so maybe they can get up and introduce themselves. Annika, Elias, Sven, and Johannes. So you have phone numbers in your conference map. So in case of emergency, so please contact us. And there will be help in this building most of the time. So feel free to contact us if you have any needs. Yes, and you will get a lot of help and attention from our staff, Frau Gabler, here she is, and Frau Dingenotte, and Frau Abrams from the Clay Mathematics Institute. All right. Well, thank you. And now we'll start with a short introduction. Introduction to arithmetic geometry in Göttingen. So first of all, here are the organizers of this school. Jim Carlson from the Clay Mathematics Institute, Henry Darmon, he will be here starting next week. So David Elwood, Brandon Hassett, and myself. And here, one more time, our staff, Frau Dingenotte, Frau Gabler, Herr Kohlspal, responsible for computers, and Dr. Wiedmann. A little bit about the history of the University of Göttingen. So it was founded in 1734 by George II. He was the father of the King George, the mad King George. So now we've seen a movie about it, so now we know all the history. And he happened to be a king of, Great Britain and simultaneously of Hanover. So, and he was quite international in this respect, and he founded the university, and it was opened in 1737. So here we can see his very distinguished face, first on a contemporary painting, then on a coin, and eventually he himself on the university seal. So here are a few buildings. The old auditorium, built old but built much later. Maybe I can show you. And this is the president's office and the main lecture hall of the university. And this is the new library, the new building of the library. Now, the university started with 4 departments, 4 faculties, and a few students. And in the 19th century, there were about 1,500 students here. Around 1900, there were still between 1,500 and 2,000 students. But after the First World War, the student population grew very significantly. I should also say a few things about the library. Now, the Göttingen Library is designated as a national repository of mathematics. So it's so-called Sondersammelgebiet. So it has a grant, and also it's charged by the federal government to collect everything that gets published in mathematics. So it's in this new building where you have one of the most complete collections of mathematics in Germany. In addition to that, our institute has books and journals, especially the old journals are quite complete. From number 1, you can look it up in the library in our building. So we have about 50,000 volumes here. All right. So more about history. 100 years after the university was founded, there was a big event, namely the expulsion of the famous 7 professors in Göttingen. Now, so here are the names. I should tell you a little bit more about the historical background of that. So what happened is that the son of the King George the Mad and the grandson of the King George who founded the university, he died. And after he died, there were some legal perturbations in England which resulted in the Queen Victoria becoming the Queen of England. But at the same time, the succession of Hanover and the kingdom here, well, it wasn't quite as straightforward. And somebody called Ernest Augustus became the ruler of Hanover. Now, it was quite a competition, and apparently he left England in a hurry, which is depicted on this coin. So here you can read to Hanover 1837. Well, maybe you can't read it, but that's what's written here. And you see him on a horse, very much in a hurry. And on the other side of the coin, you see the Queen Victoria, who looks quite happy and is beaming with excitement and anticipation. And now he came here in 1837, and so the first thing he did, he got rid of the constitution, the liberal constitution. Now, the professors, of course, disagreed and opposed it. So he told them, "You're fired." And that was the end of it. And 7 of them had to leave the University of Göttingen, and some of them didn't find employment for many years to come. Now, how is that related to mathematics? Well, one of the professors, Ewald, he was an Orientalist. He was a son-in-law of Gauss. And another professor here, Weber, he was a close collaborator of Gauss. In fact, Gauss and Weber invented the telegraph and built the first functioning telegraph between linking the Gauss Observatory and the City Hall. And some others are also quite important. So we see the brothers Grimm. So in fact, I'm not sure you know it, but right here in Göttingen we have the enchanted forest where the Red Riding Hood used to spend her afternoons. And it's right here. You can just go up the hill, and it's quite a big forest. And yes, so you should certainly take a look. Now, so this is the brothers Grimm on 1,000 Deutschmark, and Gauss made it only onto 10 Deutschmark. And I have the note in my pocket here, so I can show you. All right, so today we have 13 schools. Göttingen is a university of about 24,000 students, and it has 315 professors right now, plus about 120 at the medical school. There are very few professors here. In the math department, in the pure math department, we have 6 full and 3 associate professors for a school of 24,000. We have the University of Göttingen has about 10,000 technical administrative staff. There are some medium-sized companies, spin-offs of the university located in the city of Göttingen, and you can find out more about Göttingen if you go to some web pages here. Now, Göttingen was most known, like in the 20th century, it was a really famous university. It was most known for physics, mathematics and physics. In fact, so in the 20s and 30s, many Nobel Prizes went to the University of Göttingen, and a few names are listed here. Altogether 44 Nobel Prize awards, and like one of the buildings here, so this is the building. It's right next to the Math Institute. It's about 100 feet from the Math Institute. You see it on the other side. So the next building on the other side is this. And 19 Nobel Prize winners worked in that building. So right now it's being remodeled and renovated. And so this is the old Physics Institute next to it. And that you can also see if you just go to the other side of the building. So here are a few names: Max von Laue, Max Planck, Frank Nernst. So that's the Physics Institute one more time. So we are Bunsenstrasse 3 to 5. This is Bunsenstrasse 7 to 9. Across the street, I don't have a picture of that here, but across the street is the German version of NASA, the space agency, a big institute with lots of equipment, and they have big machines which sort of model re-entry temperatures for space vehicles, re-entry into the Earth's atmosphere, make a lot of noise and explosions, and a lot of heat gets generated over there. They also have another machine which they built, which is unique. It's a 100 million euro machine which generates 0.4 Kelvin temperatures and like zero pressure to study some propulsion jets in space, outer space. So only here in Göttingen. Anyway, so that's what we have. There are some more names: Pauli, Bohr, Neher, writer Günter Grass. So the Mathematics Institute. So you all found your way here. So that's good news. So that's the building. So the building was built with Rockefeller funding. There was a competition between Princeton University and University of Göttingen for a big grant, and Göttingen won. And so there 350,000 Deutschmarks, were given. But you see, it's not straightforward. You get a grant, but you have to have a commitment locally. So the big negotiation was with the Ministry of Education regarding maintenance of the building. So one thing is to build, another thing is to maintain. So in any event, that's a historical building, and you are sitting on all these historical chairs, and these are historical chairs and tables here, and we have pictures, Hilbert lecturing from here. So right from here. Now, that's the library, which you'll find on this floor. There's lots of space. Again, the furniture and everything is quite original. So when I first came here, it was really amazing to see the old literature, old books and old journals. So it's quite a complete collection, so quite spectacular. So take the opportunity to take a look. Some of the old manuscripts we have put out in these cases under the glass right here. So you find lecture notes of Hilbert's number theory lectures written by Courant. So there is a proof that he knew something about number theory, at least when he was in Göttingen. There are lectures by Klepsch. There are old manuscripts, the Riemann's lecture notes here. And in the library, you can find, it's under lock, but you can ask and you'll see a complete set of lecture notes from Hilbert's lectures. From the very first year he became professor until the very end, every semester, all the lectures he gives, they are written down by assistants, and there is a complete record, as well as seminars organized by Klein. So with entries by Planck and Horwitz and Lindemann and all the classics. So that's the library. The entrance hall is called the Hilbert space. Now, there is a Hilbert right there. So there is a Gauss lab, so there is at least some terminals you can see right away, but we have more. The barbecue is happening right here, sort of on the other side of the building, in the garden. And we have a collection of mathematical models which was initiated by Klein, and so for us the most relevant are, of course, cubic surfaces. There is a big collection of cubic surfaces, smooth ones and singular ones. In fact, the very first year Klein was appointed professor at the age of 23 in Erlangen. So one of the seminars, the title of the talk is a presentation of a model of a cubic surface with 4 singularities. So, one of the spin-offs was then a company which was building these models, like mass producing them and shipping them off. And I know that Columbia has a collection. So some universities in the States have those models in their possession. Anyway, so we have an exercise room, exercises. So on your schedule, you find that every day around 5:30 we have exercises. So now, so it's ambiguous on purpose. Yeah, some of you may just want to run around the building and up the hill and down the hill, so that's fine. But we have prepared sort of computer classes, so exchanges. You can meet in small groups. You can discuss the lectures of the day, or so that's a time for exercises. And there is a big room which was also designed, of course, by Courant and Neugebauer, but sort of envisioned by Klein, a large room for exercises for a big group. So, and like 200 people could probably do their homework right there. And there are several blackboards, original blackboards, and the assistants and professors would go from table to table and ask, so what are your difficulties? So we have a cafeteria in the basement where you can get something to drink or eat. All right. Now we come to arithmetic geometry in Göttingen. Now, I mean, it would have been nice if, Fermat and Diophantus had spent any time in Göttingen. But in any event, so this is, let's say, the second publication of works of Diophantus. And the first one, so the first after, published in the Middle Ages around 1650, I think. So Fermat had this first publication by, I think, Bachet, and this is where he made his comments about, well, I don't have enough space to prove this, Fermat's last theorem, so to speak, yeah. But he had enough space to implement descent on elliptic curves, for example, and many other things on these margins. And after his death in 1665, so his son collected those comments and published the second edition with Bachet, and so this appeared in 1670. So this is the first published book with Fermat's sort of theorem in it, and we have it, and it's right here in the glass, under the glass in our exhibition. You can take a look. Gauss spent many years in Göttingen, studied here, became professor of astronomy here. Even today, the astronomers think that he is actually an astronomer, and mathematics was just his spare time and should not be mentioned. But so we differ on that subject. In any event, the Gauss Observatory is maybe 10 minutes up the street from here, so this way you should definitely see it. Gauss did arithmetic geometry. Of course, his 17 gone. Okay, so it's maybe cyclotomy, but one thing about Gauss's version of arithmetic geometry is that he insisted on not using any plots. So there is a letter from him to Olbers, the astronomer. So the astronomer is pushing him to reveal how he had calculated the coordinates of this Ceres, a planetoid, the rediscovery of which made Gauss famous, very young age. Well, and so Gauss says, I won't tell you, and the method, I don't have the best approach yet, and I'm still working on it. So the usual thing, back and forth, and in the end, so Olbers keeps pushing, and Gauss replies, okay, this is how I did it. And then there is a comment in brackets. I've never drawn a graph of this function, or I've never drawn even like a little drawing for that. So he somehow insisted on visualizing data in like numbers, yeah, so no geometry. In fact, that's the thing. We had a seminar on the history of mathematics here, and about Diophantus, right? And Diophant in geometry. And so we asked this expert, is there any geometry in Diophantus? And he says, no, it's all algebra. Just algebra. It's like no drawings, no nothing. It's pure algebra. But of course, when you look at some of these algebra, right, the famous thing, how to parameterize points on a conic, right, x squared plus y squared is z squared. Okay, you could say it's algebra, he finds a nice substitution. But of course, we all know that it's geometry. It's just that he doesn't want to say it. It's like in Grothendieck, there is no geometry, it's just algebra, right, or something. But so that's the issue. What's algebra? What's geometry? I mean, its boundaries are kind of in a flux. In any event, so I was looking for something more relevant than cyclotomy, and I found in like Gauss's collected works a certain equation which goes like this: x cubed plus ny cubed plus nz cubed minus 3n xyz equals to 1. So I say there are two typos here. First of all, who would write nn? Right? I mean, if he writes x cubed, he wouldn't write nn. And secondly, maybe it should not be 1, it should be 0. And then we would certainly have a Markov's equation, right, for n equals 1. So, or maybe not. It should be squares. Is it squares? Anyway, so Gauss was clearly interested in rational points somewhere, or integral points, yeah. Theorem, formarum, cubicarum, I mean, so that's Gauss. Now, Gauss' successor in Göttingen was Dirichlet, and his advisors were Poisson and Fourier. So analysis, right? Just analysis. However, he became famous for his work on Fermat's last theorem. He proved it in a certain case for exponent 5. That was his first publication, and in fact his thesis. And it's sort of funny to see a thesis with advisors Poisson and Fourier on Fermat's last theorem. But he continued to work in analysis, and we know Dirichlet's theorem on distribution of primes, and he made contributions to Fourier series, the Dirichlet kernel, and differential equations. He had several students, Eisenstein, Kronecker, Lipschitz are good names. Now, so this is his thesis, this memoir, which appeared in France here, presented at the Academy of Sciences, and that was his entry into mathematics. Hilbert, now his thesis advisor was Lindemann, transcendence of pi, and the thesis was on invariance. Hilbert worked in many fields of mathematics and started out with invariance theory, then algebraic number theory, and then integral equations, mathematical physics, foundations of mathematics. So among his students are, well, again, he had many students, but the most famous ones are probably Kurendeen, Haar, Hecke, Kneser, Neugebauer, Schmidt, and Weil. And Hilbert was interested in arithmetic questions, so Waring's problem, the solution of the Waring's problem, every n can be written as a sum of d powers with sufficiently many summons. So this is in 1909. Minkowski, a friend of Hilbert from their early days in Königsberg, also studied with Lindemann, became very famous at an early age, resolving problem posed by Eisenstein on representations of integers as sum of squares. Worked on quadratic forms that won him a prize of the French Academy and made him famous all over Germany at an early age, again 17, so worked in Diophantine approximation, geometry of numbers, polytopes, mathematical physics. Had few students. One official student, Caratadori, and there is an unofficial student, Einstein. So apparently, so he went to Minkowski's lectures in Zurich, and Minkowski didn't have a high opinion of him. He said, "Oh, well, I would never have thought that, he would amount to anything in mathematics." And so here is Minkowski's paper on quadratic forms, presented to the Academy of Sciences. There was, of course, a problem that it was supposed to be in French, but he didn't manage. He said, "I don't have the time to translate it into French. Here is a German version." And and only the letter is in French. I have the honor to submit this paper, and I hope you will still consider it. So they did. So Hermann Weyl studied with Hilbert here in Göttingen and worked on integral equations, mostly functional analysis, group theory, mathematical physics, representation theory, differential geometry. Had very few students, and in fact, the one student we know, I mean, he had like 4 students. One of them is MacLean, and when you read MacLean's book on his time in Göttingen, then you realize MacLean was here like around 1930. So you realize that maybe Weyl was not really involved in supervising that particular thesis on logic of all matters. And all right. So that's that. But even Weyl had interest in arithmetic, and in fact, Weyl's estimates will be important in one of the courses, namely the circle method. So how to estimate exponential sums. Sum, say, x from 1 to b, e to pi I alpha x to the d. So to get non-trivial bounds, depending on how closely you can approximate alpha by rational numbers with small denominators. That's an essential ingredient in analytic number theory and sort of at the core of our estimates there. And somehow it came out of his interests in physics. I mean, I don't know, something oscillating and what happens and this and the other. Hasse. All right, so Hasse came to Göttingen as a student, and then he went to the library, I guess this library, and then he started reading a book, namely the book by Hensel about periodic numbers. So we have the book. So that original book is still here. And I had it in my hands. So Hasse had it in his hands. So just go and look under Hensel in the library, and then you find the book. And then he said, why don't I move to Marburg, which is a small German city where Hensel taught. And so he moves to Marburg, gets a thesis on about periodic numbers, and eventually becomes a successor of Hensel in Marburg, 1930. He comes back to Göttingen in 1935 as a full professor. So Hasse is known for the Hasse principle, quadratics, and the local global principle. We'll hear more about it in a course by Professor Crash. He computed the Brauer group of number fields, proved Riemann conjecture for elliptic curves of finite fields, worked on abelian class field theory. He had some students, so I wrote down to Reichert and Roquette. And this is a famous paper on the representation of numbers by quadratic forms and arbitrary algebraic number fields. Siegel, again, he is interested in quadratic forms. In fact, when you look up the paper by Hasse, so this one, so it starts with, in recent times, Herr Siegel looked at representations of numbers by quadratic forms, or Siegel representations by quadratic forms, and so the starting point is Siegel's work, and then comes sort of the general algebraic approach, the Hasse principle, while Siegel moves into another direction, namely into the analytic direction, and eventually Siegel-Weyl formula and study of algebraic groups and automorphic forms, but his sort of early contribution was exactly to quadratic forms, which, as you can see, can be traced back, Gauss anyway, but Minkowski and even Hilbert. You look up his lectures in our library, and there is a course which is called Quadratic Forms and Infinitely Many Variables. So any idea what that is? So that's Hilbert's basis, right? So, but there's a theory of quadratic forms. So it was very much in their heads that, there is this quadratic forms business, and then you sort of apply it to physics, to number theory, this, that, and the other. Anyway, one of the best results of Siegel is his proof that an affine curve of genus bigger than 1 has finitely many integral points. So he had students, Kling and Mahler. He spent 10 years in no more than 10 years in Princeton at the Institute of Advanced Study, and then came back to Göttingen in 1951 and worked in Göttingen for the last couple of years. So I wrote down 3 students. In fact, he only had 5 in total. So, and this is his paper, the equation ax to some power minus b to some power is c. And so in the theory of algebraic Diophantine equations with 2 unknowns, so 2 proved important results. And so here is development of that and Siegel's theorem, and we'll hear about it. There was quite a controversy between Siegel and Lenk, and I should mention that too. So let me read this to you and then comment. So when I first saw Lenk's Diophantine geometry about a year, I was disgusted with the way in which my own contributions to the subject had been disfigured and made unintelligible. My feeling is very well expressed when you mention Rip van Winkle. The whole style of the author contradicts the sense of simplicity and honesty which we admire in the works of the masters in number theory, Lagrange, Gauss, or on a smaller scale, of course, Hardy and Landau, colleague of Siegel. Just now, Lenk has published another book on algebraic numbers, which, in my opinion, is still worse than the former one. I see a pig broken into a beautiful garden and rooting up all flowers and trees. I am afraid that mathematics will perish before the end of this century if the present trend for senseless abstraction, as I call it, theory of the empty set, cannot be blocked up. Yeah, it's difficult, yeah. Well, as you can see, these German professors, have strong opinions and don't hesitate to articulate them. In any event, and he hasn't even read, I bet he hasn't read algebraic geometry. I mean, foundations of algebraic geometry or anything like this. I mean, Lenk. So, yes. So Lenk commented on this letter naturally in writing in the notices. You can read it. And mathematics is alive and well. And in fact, derived algebraic geometry, these new developments, talk about abstractions. So abstractions are just coming and coming. And there is no way to block them. So this is how things grow and get digested, absorbed, and then something happens. In fact, it's really interesting because Siegel and Lenk, they seem to be quite similar in personality. So, well, one technical detail, both were not married, and both had very few students. And they were quite outspoken. So we have a written record of Siegel's being outspoken, but those who know Lenk, and some of us know Lenk, Professor Hassett studied with Lenk at Yale, and Lenk could be very loud on occasion, and also quite forceful in his writing as well. Well, so that's the thing. It's like a basic misunderstanding, in this regard. But anyway, I think I should have mentioned that. Now, Max Deuring was in Göttingen, so these are the years, 26 to 30, and then as a professor, 50 to 76. So he worked on elliptic curves over finite fields and complex multiplication, and in Professor Darmon's course I'm sure we'll hear more about these constructions, proof of Wales conjecture, about the zeta function of elliptic curves for elliptic curves with complex multiplication, and then eventually special values, singular moduli, which led to the work of Gross-Zagier, of which will also be mentioned. So he had many students, and you can see in this picture, very friendly, gentleman, quite relaxed. And so some of his students are Draxel, Kircher, Niemeyer, and altogether 40 students. In any event, so in the library you find, I realize you can barely read it, so his lecture notes of his lectures, so elliptic functions and algebraic numbers. So during summer term 52 in Göttingen. So that's from our library. You can look up what they were doing. Hans Grauert, complex algebraic geometry. So his thesis is characterization of holomorphy domains, Kähler metric, harmonics, subharmonic functions, like real geometer. So there's many students, but his most famous paper is Mordel's conjecture about rational points on algebraic curves and function fields. And so let me translate. So let Pn over C be the n-dimensional complex projective space, and X and Pn smooth, non-singular, irreducible curve over the field of rational numbers. So the homogeneous ideal of X and Pn is given by polynomials with coefficients rational numbers. Mordell conjectured if the genus of X is bigger than 1, then X contains at most finitely many points with rational coefficients. This conjecture has been proved only in special cases. One. Recently, Manin succeeded to show that the corresponding analog works over function fields, over complex numbers. Manin uses for his proof complicated methods from function theory. So his methods are therefore of transcendental nature, and they cannot be extended to ground fields of characteristic different from 0. In this paper, I'm going to give an algebraic proof that works in the case of any characteristic. So we see somebody in complex geometry getting involved in arithmetic and proving a major result in that. All right, so this is the introduction to mathematicians and mathematics in Göttingen. Well, I didn't mention all people we had here, the current. I mean, he did take lecture notes for Hilbert, but he worked mostly in analysis, differential equations, applications. I didn't mention, well, going back further, Klein, who, of course, was in competition with Poincaré, competition in the theory of automorphic functions. And the arithmetic ramifications of that theory, I mean, they're still very much alive today. And I think a lot of Professor Darmon's course will be devoted to modern developments arising from Klein. So we have the notes of Klein's seminars in the library, and you can just see, so theory of curves, there is a seminar conducted by Klein, Hilbert, Minkowski, where this competition with Poincaré is explained in detail, so that we have put in the exhibition. I think that's enough for now. There is going to be coffee and tea downstairs in the Hilbert space. And thank you for your attention. And once again, welcome to Göttingen.